Hi all, welcome back to Math 118. We have two main topics today, which will actually complete our studies of Chapter 1, sort of the preliminary fundamental ideas before we can start building the nature of pre-calculus on top of it. So without further ado, let's get started. We're going to jump back into looking at equations. We sort of ended last week with this idea of transforming these higher ordered polynomials and these fractional polynomials into quadratics, which then we could use our quadratic tools in order to solve. And there's two other sort of uh, archetypes of equations that we can actually use that idea on. So let me show you the first one. First one is equations of this form. Something like 1 over x cubed plus 4 over x squared plus 4 over x equals 0. Now there are some things that should kind of point us in the way of quadratic, right? We've got these three terms here, and if we could somehow factor an x out of the denominator, that would get us there. Um, that's not quite what we're going to do, but it is kind of close. If you remember back when we studied the rational expressions, right, the first thing we would do in a setup like this is we would find a common denominator. Um, and then that would allow us to write this as a single expression. So that's what we're going to do here. We have an x cubed, an x squared, and an x. It would seem to me like the lowest common denominator between these three terms would be x cubed, right? So I want to express all of these with x cubed in the denominator. And I'm going to also add the top together, right? So this 1 stays a 1. This 4, in order to get an x cubed down here, I'm going to need to multiply that by x. And for right here, I'm going to turn that into a 4x squared. All that's being divided by x cubed, and that equals 0. Now what I can do is I can actually multiply both sides by x cubed, right? Because that does not change our solutions to the equation. That's going to cross off these, and this is going to stay 0. So now we're left with 1 plus 4x plus 4x squared equals 0. This looks to me just like a perfect square, right? This is 2x plus 1 squared equals 0. So now we can take our square root of both sides, and that leaves us with the expression that 2x plus 1 equals 0, which would tell me that x equals negative 1/2. Now I do want to make sure that I check my answer, right? So let's make sure that this actually does satisfy the equation. So I have 1 over, we're checking, I have 1 over minus 1/2 cubed plus 1 over minus 1/2 squared, actually that's a 4, plus 4 over minus 1/2. And I want to make sure that this equals 0. It's going to look to me like 1 over negative 1/8, which is negative 8. Looks like 4 over 1/4, which is going to be 16, and then minus another 8, and that does indeed equal 0. So we're good. Let me give you one more example of this. Right? We're not always going to get just one solution when we convert it to a quadratic. So let's try something like, say, 3 over x minus 2 over x minus 3 equals negative 12 over x squared minus 9. So again, I want to see if I can find the least common denominator between these three expressions. This one's going to factor into an x minus 3 and an x plus 3. And we need to make sure that we have all of the terms together, right? So that would look to me like I would need an x. My x minus 3 is summed up in the x squared minus 9, and that's what I need. And so you'll notice on this one, I got everything as a single expression, right? And then I multiplied by the denominator. Instead, it is actually totally valid for me to multiply by this first, right? And when you do that, you're going to get 3. This x is going to cancel with that x, so it's going to be 3 times x squared minus 9 minus 2. This x minus 3 is going to cancel with the x minus 3 in this, so you're going to be left with x times x plus 3. And this minus 12 just has a factor of x because the x squared minus 9 cancels, so that's going to be equals negative 12x. When I expand this, we're going to get 3x squared minus 3 times 9 is 27. Looks like minus 2x squared plus 6x equals negative 12. Moving everything over and collecting like terms, it looks to me like we're going to get x squared plus 6x minus 27 equals 0. We need to factor this, so we need things that multiply to negative 27 and add to 9. That would look to me like x minus 3 and x plus 9, both equaling 0, which gives me 2 possible solutions, x equals 3 and x equals negative 9. But once again, we need to check both of these solutions just to make sure that they hold valid, right, under this equation. So I'm going to check my work here in green again. First, we'll check x equals 3. So for x equals 3, we have 3 over x minus 2 over x minus 3 is negative 12 over x squared minus 9. All of these x's should be 3's. But we have a problem here. Right here we're dividing by 0. So we're undefined, right? We can't do this operation here, so our 3 gets struck from the record. Now let's try x equals negative 9. See if that one works. Looks like we have 3 over negative 9 minus 2 over minus 9 minus 3 equals negative 12 over 9 squared minus 9. Over on the left-hand side here, this looks like it's going to be minus 1/3 plus 1/6, which is going to be negative 1 over 6. And on the right here, looks like we're going to get negative 12 over 72, which indeed also is negative 1 divided by 6. There is one more type of equation that we can solve using this method, and that is actually things that look like radicals, right? So we can take something like, say, 2x is 1 minus the square root of 2 minus x. What we can do is we can move this 1 over, and we'll get 2x minus 1 is negative the square root of 2 minus x. And if we square this whole expression, right, squaring each side, we'll get a quadratic, right? This is 2x minus 1 squared. This negative is just going to drop in the square, and so we'll get 2 minus x. When I square this left-hand side here, this is a perfect square. This is 4x squared minus 4x plus 1 is 2 minus x, which when we move that over, we get 4x squared minus 3x minus 1. This is indeed a factor that equals 0. Sorry, this is indeed a factorable expression. This is going to factor into 4x plus 1 and x minus 1 equaling 0. And so that gives me 2 candidates, right? We have x equals 1 and x is minus 1 over 4. Let's try x equals 1 first, right? We always want to check our solutions. For x equals 1, it looks like we have 2 times 1. Maybe it's equal, maybe it's not. We'll see. 1 minus the square root of 2 minus 1. So this side is going to be 0, and this side is 2 Not the case, and this one fails. Let's check x equals 1/4, or minus a quarter. Looks to me like we have 2 times negative 1/4 is negative 1/2. And that's going to be 1 minus the square root of 2 minus a quarter. 2 minus negative a quarter, sorry. And that's going to be 1 minus, it looks like that's going to be 9/4, which means we have 1 minus 3/2, which is indeed minus 1/2. So this equation, or this second answer here, the second value for x is valid. So we have our one solution for our equation. We can put a nice little box around it. One thing that I do want to remind you here of is that when we're dealing with substitutions like this, right, when we're changing things from one form into a quadratic, we always need to check our solutions, right? We end up with these things that are called extraneous solutions, right, that just kind of pop out of us transforming it into a quadratic, right? But as long as we check our solutions, right, we will always find those and be able to come up with the actual equations that do indeed solve the problem. Before we move on to sort of the next and final topic of this chapter, we want to talk about inequalities really quick. Inequalities are, in a sense, sort of the extension of an equation, right? We're trying to look at how two expressions relate to one another rather than how they equal one another. Whereas the solutions to our equations were a number of discrete values, right? Usually when we're dealing with inequalities, we end up with an interval or intervals as our solution. So let's sort of take a look at one, right? Because you do solve them very similarly to the way that you solve equations, which is sort of why they are considered a natural extension to them, right? So let's say we have the inequality 3x is less than 9x plus 4, and we want to solve this and then actually create a graph of the set of our solutions. And we're going to solve this just like how we would solve any sort of equation, right? We're going to try and isolate x on one side and some constant, some real number on the other. If we move this 9x over to this side, we're going to end up with negative 6x is less than 4. And we need to multiply both sides of this by negative 1/6 in order to isolate this x, right? Divided by negative 6, multiply by 1/6. It's the same operation. But one of the things that we need to keep in mind when we're doing this is that when you multiply an equation or an inequality, rather, by a negative number, you need to flip the sign, right? So when we divide by negative 6, so when we do that, we're going to get an x on this side, and 4 divided by negative 6, that's going to be negative 2/3, right? But as I said, since we're dealing with this negative, this sign actually flips. We get that x is greater than negative 2/3. And we do want to graph this set of solutions, right? So if we throw down a number line, let's say 0 is right there. Our point of interest is negative 2/3, and we're dealing with a set of x greater than, right? So we're going to need, let's grab purple here. It's strictly greater than, so remember we need an open circle there, and it is all of this area here, extending arbitrarily far to the right. We can also sort of take a single expression, right, or multiple expressions, and sort of trap it in between inequalities, right? And what I mean by that is a situation like this. Let's say 4 is less than or equal to 3x minus 2 is less than 13. You know, we have this expression here, and we trapped it between these two numbers here. And you could absolutely put expressions here and expressions here, But we're just sort of interested in this case right now. But we would solve this the same way that we would before. We could just sort of do two at the same time, right? If I'm going to add, say, 2 to quote both sides of the equation, now I need to add 2 here, here, and here, right? So it looks like we're going to get 6 is less than or equal to 3x is less than 15. And then when I want to divide by 3, I need to multiply all of these by 3, or divide all of these by 3. And so that looks like we're going to get 2 is less than or equal to x is less than 5. And this is also an interval, right? We'll put 0 here. And you don't need to put 0 on every number line. You just need some sets of points to kind of get a bearing, right? And we'll say put 2 there, 5 there. And so reading this, we see that x is greater than or equal to 2 and less than 5. And we're greater than or equal to on 2, so we fill in that dot. And we're strictly less than 5, and the set of those solutions is everything that's in between. The other thing that you see come into play often when you're looking at inequalities is the idea of absolute value. If we recall that something like, say the absolute value of x equals c, right? That means that x has the same quote like magnitude as c, right? Whether it's plus or minus, its distance from 0 is equal to c, right? So with that in mind, right, how can we understand something like this? Right, let's throw out a number line so we can think a little bit visually here, right? And we need our points of interest. Let's say 0, c, and minus c, right? So we know x can either be either positive, negative, or 0, right? So let's first consider the case where x is greater than or equal to 0. Well, if it's greater than or equal to 0, then these absolute value bars mean nothing, right? And we know that we're going to get this set here, right? All of the x where we're less than c and greater than 0. But what happens if x is negative, right? If x is negative, then the thing that constrains us is that its magnitude must be less than c, right? So however far it goes to the left here, however large its negativity is, it can't get larger or more negative than negative c, right? Just like we have here, the biggest it could get is negative c, but it could never equal negative c because we have strictly less than right there. So what we see here, right, is that our expression this, right, naturally becomes x is less than c and x is greater than negative c, right? This idea of an absolute value sort of naturally encodes this nested inequality here, right? And if you were to say, change this to equals, right, you would pick up these endpoints, right? This thing sort of follows almost immediately, right? Um, and we can do the same thing, and I definitely encourage you to think about this and make sure that you understand it well. Of what happens if the absolute value of x is said to be greater than c, right? What do we get? What sort of picture of what uh, inequality about x itself can we say if the absolute value of x is greater than c? Well, it turns out that this also gives us two situations, right? This says that x is either greater than c or x is less than negative c. And I know you might be tempted to also write this as a sort of nested inequality like this, But for these situations, right, where our picture is diverging, right, where you might have c here, negative c here, and x looks like this. For these sort of divergent pictures, we don't write nested things here, right? Because this is an or, right? It's either here or here, rather than giving you both this solution and that solution at the same time. But we can use these ideas, right, to solve similar problems, right? As I said, this absolute value sort of encodes the idea of these nested inequalities, so we can solve things like this, right? We can solve something like the absolute value of x minus 5 is less than 2. Using what we saw before, right, this would tell us that negative 2 is less than x minus 5, which is less than 2. And to solve this, we would do what we did before. You would add 5 to all of the sides, right? And it looks like you would get 3 is less than x is less than 7. And we can throw this on a graph nice and easy, right? You might have 3 here, 7 here, and we're looking for the set where you're less than 7 and greater than 3. And that would be right here. We're open on both sides because it's not equal to, and it's this middle area right there. You could also solve something like 3x plus 2 is greater than or equal to 4. And going off of what we said on the other page, right, this can transform us into two inequalities, right, rather than one nested inequality. It needs to become two separate inequalities, right? So we have either 3x plus 2 is greater than or equal to 4, or 3x plus 2 is less than or equal to negative 4. So we can tackle these sort of one at a time. First, starting on the left here, looks like we have 3x is greater than or equal to negative 2, which tells us that x is greater than or equal to negative 2/3. Or, looks like we have 3x is less than or equal to negative 6, or x is less than or equal to negative 2. So now we have these two inequalities that we're looking to graph together, right? Because the set of solutions to this equation is either this or that, right? So it's the union of these two intervals, right? Whereas here we have the intersection of this interval and that interval. I would say we need two important points on here, right? We need negative 2 and we need negative 2/3. And our set is everything that is either less than negative 2 or equal to negative 2. So we're going to fill in our dot. And less than tells me we're extending to the left. Or we're greater than or equal to negative 2/3, which means we're going that way.